Thank you for your attention. This will be my presentation of my trustless decentralized access control solution for the practicum. This presentation will have to be a little bit topical due to time constraints. However, please feel free to read my paper or ask questions in regard to anything you have interest in. The problem I'm addressing at its root is identity. So identity in traditional service provider world is centralized, and you can lease that identity through your credentials that you can keep as secure as you'd like. However, identity is truly in their hands. What I mean by this is exemplified by the hack a couple weeks ago of Twitter.
Elon Musk, Barack Obama, some technology companies like Apple Inc. These were just some of the famous Twitter users who fell victim to a widespread hack on Wednesday. As of Wednesday night, Twitter said it believed the hackers perpetrated the attack by targeting employees who had access to the company's internal systems and tools. What's startling about this particular hack is that so many prominent Twitter accounts, especially considering that many prominent Twitter accounts are guarded supposedly extra securely by Twitter itself, were compromised all at once. That sort of stands in contrast to other accounts which have been targeting specific individuals. Very few have the scale that today's hack had.
So as stated, many accounts were compromised um, simultaneously, and that's a fault of Twitter. That's because they had an administrative tool that 1,000 of their employees had access to, most likely an internal threat actor. Prior to July 15th, I realized that me having unmitigated access to a proprietary access control startup's data layer, proprietary source code, and network infrastructure, I hold the same power that I know other service providers do, and I can perform actions and spoof a user's identity in an unaudible way from a customer or user's perspective. So our customers have to trust that I act with integrity and operate with best security practices to ensure that their identity integrity is secure and that their application state is as expected. This need for trust concerned me. So the solution to this at its core is to remove the centralized authentication authority afforded to all these service providers and put the identity back in the hands of the users themselves. By doing so, their online identity integrity can be restored. So how is this possible? So they're leveraging a new cloud infrastructure paradigm that uses asymmetric cryptography characteristics as the basis for account authentication, allows for keys to be created on the clients, and they can be presented, and ownership of private keys can be done securely through signatures, which we all know cryptographic properties of. You can prove ownership of a private key without needing to share the key secret. This networking technology I'm referring to is blockchain. So blockchain is really an application deployment infrastructure. And some of its general characteristics are immutable transactions and records. Again, the asymmetric key usage for the basis of authentication and identity, and then strong availability characteristics thanks to its distributed nature. So looking at this technology, application deployment trends in the 2000s was the emergence of the public cloud, and in 2020 and beyond are going to be blockchain, the years of blockchain infrastructure taking precedence. However, that's not the case. A lot of the blockchain technologies that have been prevalent just can't handle the amount of throughput or load that would require real-world significant applications to leverage them. So Ethereum, for example, takes minutes for transactions to resolve. Not only that, but cost per transactions are incurred by the users making API requests. A lot of that's attributed to the proof of work consensus protocols. So enter EOS. The mainnet launched just a little over 2 years ago, and it's the first public blockchain that really has the scalability characteristics allowing for these meaningful applications to be built upon it. So it currently supports 4,000 transactions per second, in contrast to Ethereum's 12 to 15. So how does it address the problems I just mentioned? The blockchain cost per transaction is zero thanks to the delegated proof of stake consensus protocol that they use. Furthermore, the transaction time is in the order of milliseconds, whereas Ethereum, it's 6 minutes on average at best. Furthermore, managing the key management can be a concern for non-technical individuals. Private keys compromised, the identity is compromised. However, EOS automatically out of the gate supports hierarchical least privilege permissioning that allows for ease of account recovery. If the active key pair is ever compromised, the owner key pair should be kept offline and can be used for account recovery. So the solution that I built realized these technologies, and what I ended up with was a solution that cannot allow for a user's identity to be compromised due to me, who has unmitigated access to the source code, or the organization surrounding the project. Furthermore, the characteristics of EOS, scalability characteristics of EOS, has provided an application performance that's uninhibited by its blockchain decentralized nature, all at a free usage cost. So the implementation that I created is an application deployed on the EOS mainnet that has 5 public API endpoints effectively that can be interfaced with using my web app or any blockchain interface, as you'll see in my demo.
This is a demo of the application. You can see there's an authentication step that requires your wallet to be open. This is asking for its ability to sign, the wallet's ability to sign transactions on my behalf. You then get a screen looking at the access roles scoped as the user I just signed in as, which is this user. Here you can interact with the smart contract using these various actions. You can see I'll claim I'll log access to lock 1. And you'll notice that an action for me to sign will be presented via my wallet interface, where you can see the details of the transaction. I'm going to click sign, and that was a failure that came back as the blockchain's response. It said, I don't have access to lock ID 1 in the user role, which is correct. I don't have access to lock ID 1 in the user role. I have access to lock ID 1 from the admin role. So let's try this transaction again. Great, access logged, success. And you can see these actions immediately resolve on the network instantaneously. There's no delay, anything like that. See, right there, logged access. And you can see the history of the access is immutable. This is my access history from this account to these various lock IDs. Totally immutable. I, as the service provider, cannot manipulate this as I could with my current proprietary access control solution that I work on professionally. Furthermore, one can interface with the application through any blockchain interface that they desire. So one can see here, look, these are the exact same actions that I'm exposing in my web app. You don't need to use my web app to interface with my blockchain contract. You just need to have your wallet available to you. So similarly to what we just did, I'm going to log access to basically just repeat the transaction that we just did. Like I do one, roll 20 as an admin. That's why my web app makes it a little more user-friendly. We're going to push transaction. You're going to see very similar authentication. Yeah, scatter. Great. It's going to do exactly what my web app did. It's going to talk to my local scatter wallet. It's going to ask for permissions to log in and then to sign the transaction. And great. Just as with my local web app, you'll see the transaction instantaneously on-chain, all via the decentralized properties and security guarantees cover the aims of my goal. You'll even notice here the state of the application is all public and immutable as well. You can see the account holders in their keychains and the keychains from a lock's perspective.
For demonstration purposes, the other smart contract actions, we're going to claim a lock, so we're going to claim lock 89. Again, we're going to sign the transaction. Awesome. Web app, you'll then notice, great, we now have 89. So then let's share access with this new lock 89 that we have administrative rights to. Let's share access to this account at the user level. And great, it's going to prompt it again. Look at the blockchain explorer to see if the transaction resolved. And there it did. Let's say we don't have access to RazorSharp1's account. Again, you can view users' keychains totally in the clear. So you notice, look, they now have access-only lock IDs, essentially user-level lock IDs to lock 89. This is the role-based properties of my access control solution. Users cannot share keys. So furthermore, let's check RazorSharp has access. We just confirm the transaction and the blockchain state that they confirm, but you can do this programmatically so that this can be interfaced via any application, be it mobile or another web app or anything. They have this functionality available, which also is a transaction on-chain, so there's a history of the checked access in addition to the logged access. And lastly, let's revoke this user-level key that we just shared. So, fantastic. Successfully revoked. Let's check access again. And, oh, look, assertion failure. They don't have that key anymore. And if we look at the smart contract on-chain, you'll notice that key is not there anymore, along with all of the immutable transaction histories. Thank you. Great, so you saw demonstration purposes. Now for the evaluation, I was able to use my professional role to get an average customer usage scenario, and that's about 2 locks, 430 persons in the organization. So that's 860 keys. My solution currently needs about 10 bytes per key share, per key share. So that comes out to a little bit under 9 kilobytes, and with the price of a kilobyte being 13 cents at the moment, that's a little over $1 for operational costs, very affordable. Furthermore, the security of this solution is heavily reliant upon the security of the EOS network itself and the virtual machines the bytecode, the WASM operates on. However, I did a security analysis on my source code itself to see if it had any vulnerabilities that were mentioned in the security analysis paper that I read, and my conclusion was it did not. A lot of those vulnerabilities were mostly in regard to transfer value functions of the blockchain. So the outcome in the usability. So we successfully have a way to manage lock access, leveraging the security guarantees of the decentralized network that I mentioned before at a very low cost and high throughput. So the access list is stored publicly on chain and can be viewed from any blockchain explorer, as well as the access logs, all publicly and immutable. So me as a service provider cannot manipulate the state of the application or impersonate a user as they hold their credentials to authenticate themselves. In the future, I would like to work on the account management surrounding the application. Needing to have an EOS account with keys in a particular wallet is a little bit clunky. There's a lot of work around this in the overall blockchain community itself, how to onboard users more efficiently and securely. Lastly, the abstraction that's being secured right now is basically just an 8-bit integer. However, I think it would be much more useful if it was something like file hashes. So this could enforce access to something a bit more tangible than an integer at the moment. Thank you.